Going to go back to the example where we have 3 tosses of a coin, right? So we are tossing 3 coins, and here are the possible outputs or the possible sample points that we have, okay? So we can have 3 heads, 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 heads. We can have 2 heads, head, head, tails, head, tails, heads, and so on. Or no heads, like TTT, tails, 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 okay? So a random variable is a variable that we create that assigns a number to each of these outcomes. And we usually use capital letters to describe this variable, okay? So I'm going to create a variable x, capital X, and I am going to say that x is the number of heads. So x is the number of heads in a 3-toss experiment. Okay? So this is, for example, a random variable. Why is that we call this letter a variable? Well, because this letter can assume different values, right? So this variable can assume 0 if no heads turn up, right? This variable can assume 1 if just 1 heads turn up, either this way or this way. It can assume 2 if this had 2 heads turns up. Oh, I forgot this one. And so on up until 3, where 3 heads turns up. Okay? So the reason that we create these variables, they substitute the language. Before, I would say something like this: find me the probability of 3 heads turning up in a 3-toss experiment. Right? These are questions that we learned how to answer, but this nomenclature here, it's too wordy. It's not at all mathematical. So creating random variables will make our probability, our study of probability, even more mathy. But this will allow us to do interesting things with it, right? So if I created this random variable named capital X here, and X is representing the number of heads in a 3-toss experiment, I should actually, it would ease my notation, just to ask for this. Right? So both of them are the same thing. One doesn't use a random variable, and the other one does. So this one says, what's the chance, likelihood, or probability of 3 heads turning up in a 3-toss experiment? And in the bottom here, it's just, what's the probability of x equal to 3? Right? What is x? Well, x is this variable that I created that actually represents the number of heads in a 3-toss experiment. Okay? And actually, x can be 3, but x also can be 2, x also can be 1, and x also can be 0. Okay? So I'm asking you, this bottom part here is actually asking you, like, amongst all the values that x can have, what is the probability that it's equal to 3? It's just a changing in the way we address the wording. Okay? So we know that, for example, what's the probability of 3 heads coming up? Well, it's 1/8. Why is that? Well, because this is the only situation in which the heads, we have 3 heads turning up, over all 8 possible situations, right? Because you have 1, 2, 3, 4, 5, 6, 7, 8 possible situations. And it's the same thing, probability of x equal to 3. Well, if x is the number of heads, exactly the same thing. You will come here, you will find the probability where x is equal to 3. It's just 1 over all the 8 possibilities. Okay? So it's just a change in like the notation, I would say. We could ask as well, what's the probability of x equal to 2 or x equal to 3? Right? Well, x is the number of heads in this experiment. So x equal to 2, let's see. X equal to 2 is this, and this situation. So it's 1, 2, 3 over 8. Or plus, right, the probability that x is equal to 3. Well, probability that x is equal to 3, we already calculated. It's 1 over 8. So this is a half. Okay? So nothing changed by introducing this random variable. It just makes our life easier in terms of notation. Okay? Because if I were to ask this in English, I would have to do, what's the probability of 2 heads turning up or 3 heads turning up in a 3-toss experiment. And so it's crazy to do things like that. When probabilities and experiments starts being more complex, it just ruins our life to kind of have to put it this way. So we created the random variables. Okay? So random variables are just the numbers that your sample points can assume, right? So let me get rid of this. And I can't, just 1 second. All right. So in the end of the day, if we were to kind of define a random variable is a random variable assigns numbers to outcomes or to sample points, okay? And that's just it. So that you can, when you're asking the probability, you're much more, your notation is much smaller, okay? Good? All right. So, but random variables, they come up in two different flavors. They come up in 2 different types, okay? And we call this 2 different types as discrete random variables or continuous random variables, okay? We call it discrete RV or continuous RV, okay? And I want to talk a little bit more about what this means. So a discrete random variable is a variable that's representing a probabilistic experiment. We're still doing experiments, right? And this variable that we're kind of creating just assigns numbers to the outcomes. So it represents the outcomes through numbers, okay? And when you're doing an experiment, you will have values back. You don't know what value will come back, right? For example, tossing a coin, it could be heads or tails. Tossing 3 coins, it could be heads, 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 or heads, tails, heads. I don't know what is coming back because it's a probabilistic experiment. It's not deterministic. But whatever value comes back to the random variable, right? These values can be discrete or continuous. So what is a discrete value? It means that the values that are returned from that are assigned to my outcomes are isolated in a range. Okay? So these are values. A discrete value or variable is the one that can assume only specific points in a range. So let's say that I'm getting a range from 0 to 3, okay? My variable can only be 0.5, 1, 1.5, 2, 2.5. So only following these bullets here. My variable cannot assume anything out of the bullets. So my variable cannot be 1.6, for example. So the values that the variable can assume are actually islands per se. If you want to go to the next value, you have to jump, right? You have to jump. Each value is isolated, okay? This is a discrete random variable or value. Now, what is a continuous random variable? Well, a continuous random variable is the one that you don't have a bullet point. You actually have, you know, a total line where your values can live. Think about this. Imagine that I have a discrete random variable and I start making these bullet points closer and closer together, lots of bullet points. At some point, you can say that your variable can have any value in that range. So, for example, if you have a range between 0 and 3 here, your variable can be 0.32, it can be 0.33, it can be any value, it can be 2.85, it can be any value inside that range. You're not necessarily locked into the bullets that in the line, right? The bullets that appears in discrete variables. And actually, if you zoom another range, for example, I can have any value in the range 0 to 3, but if I take an interval, for example, 0.32 to 0.33, and I give a zoom, right? So 0.33 is here, 0.32 is here. Actually, I can still assume any value. I don't need to jump from 0.32 to 0.33. I can actually have a number that is 0, 32, 4, 7, 8, 9, 2, 1, 3, 7, 8. Right? I can have any value in any range. If you take two numbers, it can be smallest as you can do them small, you can still be in between them. Okay? So that's the concept of a continuous random variable. So the variable, your experiment, will return to you, has it outcomes, numbers that can be any number in between a range. Okay? And here's a thing that is curious, and actually it's good for us to know. When we measure something, for example, I want to measure the weight of a dog. So the weight of a lizard, I don't know, between 0 and 3 kilograms, right? If you put the lizard in the scale, your scale will give you a number. For example, it could give you 1.53 kilograms, okay? But if I go to the biology department and put in a supersonic whatever scale from Mars, and the scale gives you 10 digits from the decimal point, it might be that it will return 1.53, 209, 208, 13476, right? So it is the continuous variables. You can go as precise as you want. You can have any number in that line. So if you have a shooting gun and you shoot the line, wherever it lands, you can have that number. Whereas in your discrete random variable, if you shoot the line and you don't hit the bullet, point, you don't exist, right? So And this is quite interesting because when we learn about continuous random variables, we kind of we understand that actually our measurements in the world are never what it had to be, right? So if you're measuring the weight of the lizard, you cannot tell how many electrons and how much mass it exactly. We don't have this granularity. We don't have this effectiveness in measuring. So whatever we're measuring, we can go very precise, but we're never going to hit the number precisely. Okay? Cool? All right. So I'm going to give you some examples of what are like discrete and continuous random variables in our experiments. So let's say I'm calling x. It's a capital letter, right? So it's a random variables are represented by capital letters. Oh, this is important. You can call x, y, w, whatever you want, but you cannot call capital Z, okay? So random variables you cannot use capital Z. Capital Z means something else. Capital Z is the standard distribution. We will see this, but you cannot assign variable Z to any kind of experiment, okay? So what I'm telling you is that x is a random variable that represents a toss of a coin, right? So x is a toss of a fair coin. So this x will return some values, right? You can have two outcomes. You can have A and T, right? And I'm telling you that my x will be 1 if a heads turn up, and it will assume 0 if if tails turns up. Okay? So again, I'm just creating a variable that is mathematizing even more my life, because before it was heads and tails. It's English. Now it's 1 or 0. 1 representing heads, 0 representing tails. Okay? And my question is this a discrete random variable or a continuous random variable? Yeah. It's a discrete. Why? Because in this interval of 0 and 1, you can only assume 0, and you can only assume 1. There's no outcome such as 0.43, right? No, the outcomes must be 0 or be 1. There's no in between them. So you are locked into these bullet points in the line, okay? So this is a discrete experiment, a discrete random variable. Now, let's think about here. I just messed up here. Okay, so this is I'm defining a variable, a new variable, a y, a capital Y, so it's a random variable. And I'm telling you that this variable represents the mass of an animal in the Toronto Zoo, right? Okay, fine. It's the mass. So you have like, I don't know, maybe you have an ant walking like in the zoo, and it's like its mass is very close to 0, right? And maybe you will go up until the heaviest animal in the zoo. It's an elephant, maybe like 3,000 kilograms or something like that. Okay, so 3 tons. So the thing is, if you get, for example, if you choose an animal, the weight of the animal, the mass of that animal can actually be anything. You're not locked into a specific value in this range. So let's say that you get a lion. So you go to the lion's cage. Hopefully he is down. You get him and put him in a scale, right? Your scale is never precise as it could be. Like, you can always be more precise, but let's say that it returns 132.85 kilograms. Okay, it's just I'm just guessing the weight of I think it's more than this, but anyway. So it doesn't matter which animal. You can get you could get a Brazilian capybara, right? A Brazilian capybara, maybe 70 kilos. I don't know. 70.3321. I don't care. Wherever you shoot in this range, you can land and that's fine. Okay? And you can still go precise as much as you can. So what type of variable is this? Continuous, right? Continuous random. So this is a continuous probabilistic experiment. You're doing an experiment. For example, my experiment is going to the zoo tomorrow in Toronto and getting an animal and weighting the animal, right? And I know that this is a continuous variable. So I can actually now do answer questions as this. What's the probability of the mass of an animal in the Toronto Zoo is bigger or equal than 2,000 kilograms? See how simple it is, the notation right now? Right? So it's just P of Y, which represents the mass of the animal, bigger or equal to something. Okay? So I can ask questions from my experiment in an easier way. Okay? Now, the last example that I want to give you is this. I am creating a random variable W that represents the number of ants born after this moment in time, after today. Okay, so this is an experiment I'm doing. I'm somehow measuring how many ants are born, and this is a probabilistic experiment, right? It could return 0. Maybe something happened, a meteor hit Earth and no ants are reproducing. They went crazy with some kind of mental health crisis for ants. I don't know, but they're not reproducing. Or it could be 1 trillion. I don't know. It could be whatever number, right? But is this discrete or is this continuous? It's discrete, right? Although you can have a big range, like from 0 ants reproducing up until, like, I don't know, infinity ants reproducing, lots of ants reproducing, I don't know, 1 trillion ants reproducing, you cannot be free to live in the line wherever you want. You will have to be 1, 2, 3, 4. So whatever number comes back from your experiment, you cannot have 1.5 ants born. You will have to jump into little islands in the line. That's 1 by 1, because ants are born 1 by 1, right? You're counting 1 by 1. Okay? So this is also a discrete random variable. And I can also pose questions like, okay, what's the probability of the number of ants born after today be, I don't know, more than 2,000 and less than, I don't know, 1 million. Okay? So look at how easy is the notation right now. It's just the probability of W. It's a letter, which is a variable. And obviously that W can value anything between 0 and a trillion. So you have a probability that W will be in between 0 and a trillion. But obviously that I would say with I'm confident that having a 1 as an answer, meaning the number of ants that are born today, will be very low, right? Because right now, this moment, an anthill might be producing 2,000 ants, right? Good? All right, so this is random variables. This is just It's just this. It was just to ease notation. But because of that, because of doing a mathematical notation, now we can go further into doing stuff with it, okay? So the first thing that we're going to see is what we call probability distribution functions. Who is in stats, I think already saw this. I will call it from now on PDFs. It's not the file in your computer. It's a probability distribution function, okay? So this is PDFs. Let's go talk a little bit more about PDFs. So PDFs, what is the definition of PDF? Well, PDF is a function that lists the values that your random variable can assume, and they are associate probability. Okay? So I'm going to write this down. So a PDF is actually a table. It's a table. It's just simply a table that lists the values a random variable x can assume and their associate probability. So this is the definition of PDF. Okay, let's break this down, okay? So let's go back to our experiment where x, it was x was the number of heads on a 3-toss experiment. Okay? So here are the outputs that we had. The heads, 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 tails, heads, tails, and the number that this variable x could assume, right? If heads, heads, heads turned out to be the outcome, my variable would assume 3, okay? If this one was the outcome, it would be 2, and so on, okay? So the PDF is just a way to summarize. It's just a way to summarize all you need to know about the probabilities of a random variable. So it is like this. It's a table, and in this table we have 2 columns. The column on the right, on the left, lists the values that x can assume. Okay? So what are the values that x can assume here in this experiment? It can assume 0 if it's TTT. It can assume 1, 1, 2, 1, 2, 3. So in the end of the day, your variable can be 1, 0, 1, 2, or 3. These are the 3 numbers that your variable can assume, right? And usually you will see this column with a little x. You can see that, so my capital X is like this. My little x is like that, okay? So you will usually see a little x in that column, meaning that these little x are the values, you're listing the values that your random variable, which is capital X, can assume, okay? So you have a capital X is your random variable. It represents the outcomes of your experiment, and it actually can assume little x, which is, it could be 0, 1, 2, or 3. Okay? Now, the PDF has another column, and the other column is called, you will see this other column like this. It's the probability that your random variable, which is capital X, equals the little x, the value, right? So it's just we're going to learn how to navigate through this table. But in the end of the day, what the PDF is is it lists the values that you can assume and their respective probabilities. So here, in this part of the table, this will be actually the probability of x being equal to little x. In this row, in this particular row, little x is 0. So here should appear the probability that your variable is 0. In the next row, the value that will appear will be the probability of x being equal to 1. Here will be the probability of x being equal to 2. And here will be the probability of x being equal to 3. Okay? So it's a table where you can retrieve things, right? You take a look at, in this column, you're taking a look at the probabilities. And to find whatever the value that you're asking for, you look at the rows. So if I ask you, what's the probability of your random variable being equal to 2? Well, this is the value. It's in this row, because in this row, little x assumes 2, and you read here the probability of x being equal to 2. Okay? So let's build up this probability here. So I was just showing you the structure. Now let's do it a real PDF with our example of the coin, the three toss experiment. Okay? What's the probability of my toss experiment returns a 0 value? I'm in this line here. What's the probability of x equal to 0? Well, for x to be 0, the experiment has to kind of output TTT, right? So it's just TTT, which is 1 over 8. You have one experiment over 8 possible, one experiment that interests you over 8 possible experiments. Okay? So in the end of the day, asking P of x equals 0, right? I'm completing these numbers here. P of x equals 0 is actually the same thing as asking probability of having tails, tails, tails in a 3-toss experiment, right? What's the probability? Now the second line, let's go and complete this. What's the probability of my random variable equal 1? Who wants to try? 3 over 8, right? So you have this outcome, and this outcome valid. So you have 3 outcomes over 8 possible outcomes. Okay? So it would be the same thing as asking, what's the probability of having 1 heads turned up in a 3-toss experiment? Okay? So just x equal to 1 makes your life easier, and you will just populate the table. Okay? What's the probability of x being equal to 2? 3/8, right? Why? Well, because this is equal to 2. X here, so this is the value that the capital X are the values that it can assume. 1, 2, 3 experiments over 8 experiments. Okay? And finally, what's the probability of x being equal to 3? Well, it's 1 over 8. Because this is the only case here. Oops, sorry. This is the only case here that we have 3 heads, right? And that's it. This is PDF. It's a table that summarizes all the probabilities that you need. And you should know how to read the table, right? So if I ask you what's the probability of x being equal to 3, you should know that actually the probabilities are here in the second column, and you just need to find when my little x is equal to 3, and you can just go to the specific row. Well, your x is equal to 3 in this row, so here's my probability. It's just 1 over 8. Okay? Questions? Everything good with PDFs? All right, cool. So let's do a very easy PDF just to kind of practice. I'm calling a random variable y the toss of a fair coin. Okay? And we know, and I'm assigning 0 if it comes back tails, and 1 if it comes back heads. Okay? So this is just a single toss. Well, we know that our outputs could be heads or tails. So my random variable here, if it's heads, my random variable will assume 1. And if it's tails, my random variable will assume 0. Okay? How can we do this PDF? Remember, it's a table. So we start by doing a 2-column table where on the left I have to list the values that my variable can assume. In this case, oh, it's not x, it's little y, it's y. So this will be little y. Little y represents the values, right? So the values that I can assume is 0 and 1. Okay? And in the other column, you will find the values that appear in the other column are actually the probability of your y being equal to your little y, right? So in this line, if your little y is 0, what probability should come here? The probability that y equals to 0, which is, in this case of a fair toss experiment, is, what's the chance of having a tails in a fair coin experiment? A half, right? It's 1 over 2. It's just this over the 2 possible experiments. And what value should we put here? Well, here is the probability of your y being equal to little y, and particularly this row, your little y is 1. So this is the probability. And in a fair coin experiment, this is also a half. Okay? This is the PDF of a fair coin experiment. Okay? Sometimes we will see PDFs not as tables but as graphs. Sometimes you will see something like this. We will have a lecture on this. Don't worry. But we call this histograms. So people who are in statistics, very often we see the table translated in a graph, meaning that you look at this graph and you know that your random variable can be only 0 and 1. So you're kind of talking about a discrete variable, and it will appear some kind of some boxes, and these boxes will bring up you a value, right? In the end of the day, we will see that you have to multiply by the base. This will give you the probability, but sometimes you will see a value that will kind of give you the probability. You have to tweak a little thing, but this graph is the same thing as the table. It's telling you the same thing, okay? That the probability of being 0 is a half and the probability of being 1 is a half, okay? Cool? But again, we're not seeing this yet. Not seeing this yet. We're going to learn how to do the histograms with more rigor. I'm just telling you that you can see PDFs with graphs. Okay, questions about PDFs? We're good? All right. Let me see just one thing here. What's... Okay. Yeah, so this is just an exercise where we have here underneath here, we have the coin experiment, the 3-toss experiment. Okay? But I'm just taking it away because I'm presenting you the results through a PDF. Right? PDF is all that you need in terms of probability. So in this experiment, where X is the number of heads, we already calculated this. This is the PDF. Okay. So we can ask questions. We can ask questions. So for example, the probability of X being equal to 2 or X equal 1, right? What is that I'm asking? Well, it's the probability of having 1 heads up or 2 heads up, right? And if you have the table, you just go and retrieve these values from the table. So what's the probability of X being equal to 2? Well, the probability of X being equal to 2 is equal to 3/8. Or the probability of X being equal to 1 is actually 3/8. So this is 6/8 or 3/4. Okay? How do you do that? Well, what's the probability of X being equal to 2? Just come in the table. Find the row where your little x, your value is 2, so that this becomes 2. And then just retrieve the value here. Okay? That's 3/8. What about X equal to 1? Well, go in this line because little x is equal to 1, meaning that the value that is printed here will be X equal to 1. It's exactly what you want, and it's 3/8. Okay? I can ask you another question. For example, the P of X different than 2. Well, what is X different than 2? So you can think about this. In your experiment, it's having this line, and not this one and this one, right? So you can think and just look and sum up that thing. So it's the probability of X equal to 0 plus the probability of X being equal to 1 plus the probability of X being equal to 3, right? All of this represents the probability that I don't have 2. And you can just sum up. This is 1/8 plus 3/8 plus 1/8. This is 5/8, right? Okay, you can do that. So it's really summarized. I don't even need to kind of tell you a story of what experiment I'm doing. This is all you can have. It's summarized. All the probabilities are there. You just need to look. Okay, that's why it's so important. Now, here's the thing. You could also think about the probability of not being 2 as what? Well, think about this. Do you agree that these are the values that my random variable can assume, right? They're all accounted for, right? So if you think about it, 1/8 plus 3/8 plus 3/8 plus 1/8 has to sum up to 1, right? Why? Because these are all the possible outcomes. You have all the possible outcomes. This is your sample space, right? So in the end of the day, you can use the same formula with the table that we learned past weeks. So you can have 1 minus the probability of X equal to 2. It's the same thing. It's just I'm telling you that it applies to the table as well, right? So not being 2, you can look at the table. Because this table is accounting for every sample point, this is your sample space, and you can just use the formula. So everything in this, if you sum up the probabilities, it should be 1, but you're removing this line here. You're removing the line of little x equal to 2. So in the end of the day, you just go to, well, remove the line where the probability x is equal to 2. So I have to find the value in this column where my little x here is 2. Where is my little x? Where's the row where my little x is 2? Oh, it's this one. So the probability appears here, it's 3/8. And you will have 1 is 8/8 minus 3/8. It's 5/8. As should be, right? It should be the same result from doing the sum. Okay? Yeah.
Is it possible to like do this table with continuous values?
Yeah. But then it doesn't, the name is not probability distribution function. The name is probability density function. We will see it a little bit. Okay? Good? All right, that's it. That's it. That's PDFs. Okay? And you will see that in the test, you will have PDFs for you to complete. You will have PDFs for you to retrieve values. So it's very important for you to know how to read and kind of construct PDFs. Okay? All right. So, just 1 second, guys. Just 1 second. Okay, so if you think about the PDF, right? The PDF, the probability distribution function. The PDF has a column, little x, and p of x equal little x, right? Cool. Now, sometimes we want to ask questions such as, what's the probability of x being greater than, I don't know, greater or equal than 4, right? Well, if you had to use the PDF, and you can, PDFs are all you need. But if you have to use the PDF, imagine that we had a PDF where it starts in 0, and it goes to 1 trillion, right? So it could be the number of ants born. And I'm going to ask you, what's the probability of that you have more than 4 ants born? What you would do is you would have to get this line, that line, that line, and keep summing up the numbers that appear here, right? You could be a little bit more smart and say, well, this is 1 minus this block, but even then, it's too much trouble, right? Because when you're tossing a coin, or 3 times tossing, this is an experiment that is very like engineered for teaching, because this is not something that happens in the real life. Real life is examples like this. Your random variable can go from 0 to 1 trillion. And then you're left with lots of work. So there's another type of table named the cumulative distribution function. Okay? And we're going to call it from now on the CDF. So we saw the PDF. Now we're going to see the CDF. Okay? And this table actually helps us to answer these types of questions. Oh, what's the probability, for example, that x is less than or equal to 2? Or what's the probability of x being more than 5? What's the probability of x being more than 0.95? I don't know, like questions with less than or greater than. Okay, so questions with less than or greater than. So it's just a way to help us and ease a little bit the probability, the PDF, right? Okay? And here, the definition of CDF is this. It's a table that gives you the value that your variable can have. So here the left-hand side is the same, right? This column here is the same. Okay, in this case, I'm showing you an experiment where my variable can range between 0 and 5. And it lists a probability as well in the second column. But some things changed slightly, right? For the PDF, the sign was equal. And here the sign is less than or equal to. Okay, so the only thing that changes is that in the PDF, you have x and p of x equal to something. Okay? And in the CDF, you have x and p of x smaller than. It's the only difference. So this is a PDF. This is a CDF. Okay? So it's the same table. It shows you the same kind of structure, but it's telling you a little bit different. That probability is a little bit different. It's telling you another thing. So for example, I want to know what's the probability of my capital X here be less than 2. How can I find this? Well, if I had the PDF, I would have to sum everything that, like all the rows with little x being less than 2. But what about here? Now here I have a CDF. How can I retrieve this value from the table? Somebody knows how to do it or want to try? No? 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 All right. So what we do is this table, whatever is printed in this column, in the second column, is giving you a probability, right? And so what we want to find is the probability where capital X is less than 2, right? So I have to go to the row. I have to find the row where the little x, the value that my variable can assume, is 2. So I get to this row. What number is printed here? Well, the number that is printed here is exactly what I want, is the probability of x being less than or equal to whatever is in the row, which is 2. Okay? So what's the probability? 0.6. Okay? It's a direct consultation to the table. Okay? I can ask you, what's the probability of x being less or equal to 4? Who wants to try now? Yeah. 0.9. Exactly. Well, how do you do it? Well, again, your little x is it's the value, right? So find the row where your little x is 4, and it's here. This is the row. And retrieve the probability. The probability of being less than that number is 0.9. Okay? So 2 simple tables that summarizes everything we need to know. PDF would be enough, but they created the CDF just to ease our life when we have greater than or smaller than. Oh, but CDFs only have the smaller than. Well, we're going to see that it's easy to, with just the smaller than, just flip and find the bigger than. Okay? So one is used to questions as equals. The other is used to greater than or equal, greater than or smaller than. Okay? Cool? All right. Now, the truth is that you actually have only the PDF is enough. That's the truth, right? And we do the CDF. We construct the CDF to ease our lives in terms of less than or more than. But the CDF is constructed from the PDF, right? So if you open a book and or if you go to the internet and you find a distribution, you will have the PDF there. And if the book doesn't give you the CDF, the other distribution, you can just do it yourself. Okay? So if you have one, you can retrieve the other. If you have the PDF, you can do the CDF. If you have the CDF, you can do the PDF. They're the same. They just changed. They tweaked it a little bit to show different things. Okay? But in our test, we need to know how to go from one to the other. Okay? So look what I did here in this slide. Take a look at this first table, right? Only the first table. I kind of merged the CDF and the PDF. Okay? So I have because they have all the same left side, right? The same first column. I put in the first column, which is similar, which is the same to both here. Here I'm showing the PDF, and here I'm showing the CDF of this little x. Okay? Cool? So I just kind of stacked the columns. All right. So what I want to do here with you guys is, so we're building, you can build the CDF from the PDF, and you also can build the PDF from the CDF. We're going to do both ways, okay? Today we're going to do just this one because of the time, okay? All right. So in the CDF, I'm telling you that x can assume -1, and when it does, the probability of x being equal to -1 is 0.4. Okay? Cool? Now, what value should I put here on, let me get rid of this. What value should I complete in my CDF? Well, look at the question. The CDF asks what's the probability of having my variable being less than or equal to -1, right? In this row here, my little x is -1. I'm working on the first row. So think about this. It would be the probability of having x equal to -1, right? Plus all the probabilities of x being less than -1. Do you agree? But do I have x's being less than -1? No. So actually, in the end of the day, the first line of a PDF and the first line of a CDF is always the same. Right? Cool? Because, well, you don't have anything smaller than 1. So this probability turns out to be that it's just the equal. And the equal you have, it's 0.4. Okay? Now, let's think about the second row. Okay, now in the second row, my little x assumes 0. So the value printed here is the probability that x equals to 0, which is 20%. Okay? What should I put here in the second row of the CDF? We're finding the CDF. Well, this here is the probability that x is less than or equal to 0. So it will be equal to 0 plus everything that's smaller than 0, which is what? -1, right? So in the end of the day, this is just this number, which is 0.2, plus what number? 0. So you have the row that you're in plus the row before you. Okay? So this number here is 0.6. What is, now let's go to this row. So now we're on this row of 1. This row tells you, the PDF tells you what's the probability of being equal to 1. Well, it's 0.3. And here, it's the probability of being less than or equal. Well, it's the probability of being equal, which we have. It's in the row. It's in the row. It's here. It's 0.3, plus everything that comes before. Do you agree? Everything that comes in the lines before, in the rows before, because it's, so, sorry, this is equal to 1. This is the probability of x being equal to 1, which is in the row, it's 0, 3, plus the probability of being x less than 1, which is 0 and minus 1. So this is 0.3. The probability of 0 is 0.2. It's indicated in the PDF, plus the probability of minus 1. It's indicated in the PDF, and it's 0.4. So in the end of the day, you're doing this plus that. This is 0.8. Okay? Now let's move on to the final row. The final row is this. What's the probability of a number being less than 2? Less or equal than 2? Well, less or equal than 2 is being equal than 2, and all the points before. So the probability of being x equal to 1, the probability of x being equal to 0, the probability of x being equal to minus 1, right? So you're taking the value on the row, which is 0.1, and you're summing up all the rows above, 0.3 plus 0.2 plus 0.4, okay? This is equal to 1, and always equal to 1. So in a PDF, the first row is equal to this. In a CDF, the first row is equal to a PDF, and the last row has to sum up is 1. Why? Well, because in the CDF, we're summing up the rows above. And if this PDF is all of my sample space, I'm summing, it will come up to 1, okay? So in our exercise, and I mean, this is very cluttered and maybe confusing. I'm going to do the same thing I did in the last section, in the other section. I'm going to redo it on the side using just like the algorithm and not explaining everything, like just the algorithm, okay? So pay attention here, because this is what you're going to have to do in the test. If you have a PDF and you want to find the CDF, the first line is equal, okay? Why? Because there's nothing less than minus 1. Then the second row, you take the number and sum to the previous one. This is 0.6, right? The other row, you take the number and you sum the other two, which is already 0.6, right? Because you did that before, right? And in the last one, it has to be 1. You don't even need to do the math. It has to be 1. Why? Because you will take 0.1 and you will sum up all the other lines. So in the end of the day, you're summing all the other lines of the PDF, and the PDF needs to sum up to 1. If you see a CDF walking and it doesn't end on 1, it's wrong. Somebody did a mistake. It's not a CDF. And if you see a PDF and you sum up its second column, it's not summing up to 1, it's a mistake. That's not a PDF. It's disguised as a PDF, but it's not a PDF. Okay? Cool? So we will do lots of exercises in the end, like of PDFs and CDFs, how do we come from one to the other. But you will see that in the end of the day, in the tests, you will be given PDFs or asked to find PDFs or CDFs. Okay? Cool? All right. So we will continue on Thursday. Thank you, guys.